Formal treatment of quantum mechanics requires this knowledge of operator algebra, eigenfunctions, eigenvalues, and a set of quantum mechanical postulates. Today, in the series of quantum mechanics, in lecture 5, I shall discuss the operators, operator algebra, and quantum mechanical operators, and also the eigenvalues and eigenfunctions. The operator, say, let me first define the operator. Operator is a mathematical instruction to be applied to a function or to a number, give a new function, a new number. Say this symbol is a square root operator. This symbol square root operator does not mean anything, but whenever I shall write some function x4 under it will give you the x square. So this is a new function. Whenever I shall put another number, it will give 2. 2 is a new number whenever it is operated by the square root on the number 4. There are so many operators in algebra. Say this is the square operator. This is d by dx operator, and this is d2 by dx square operator, and this is integration dx operator, and so on. Operator like algebra could be added, could be subtracted, could also be multiplied. For example, addition and subtraction, addition and subtraction, addition and subtraction of operators. Say a cap, one cap is given generally on the head of this symbol or the physical property. A cap plus minus b cap. This is another operator. Whenever operates on a function, always operator, any function, any operations could be done on a function, and this one gives you the a cap f plus minus b cap f. For example, say a cap equal to d by dx, and b cap is say 3x square, or a cap is suppose log a cap log e is also an operator, and b cap is equal to d by dx, and the function, let the function is x square. So whenever these two operators are added or subtracted, the result gives like as this log e plus minus this d by dx and the function x square, and this gives you this log e x square and plus minus d by dx into x square, and gives 2 log e x plus minus 2x. This is the result of this operator. This is the result for the final result of the summations of this log e and d by dx operators on this function of x square. The square of this operator, say a cap square of this operator means the same operation is done twice. Say this d by dx and x square. So say someone suppose sin x, then d by dx square equal to d by dx into d by dx, and instead of fx we can write this as sin x. Sin x. Sin x is the function we have chosen. So this one again gives dy dx and it is cos x. And whenever this cos x again operated by dy dx, it will give you this minus sin x. This operator could be also multiplied. Say multiplication of the operators. Say a cap and another b cap, and the function is fx. Then this operation is done one after another, and the order is being from right to left. So this will give you this a cap first to be operated by b cap and fx, and whenever operated it gives a new function, say gx, and when gx is operated by a cap it will give you this hx. hx is another function. The order of this operation is a very important factor in case of multiplication. Then we come with commutator, or I can say quantum mechanical operators. Quantum mechanical operators, or the operators which are used in quantum mechanics. One is linear operator. All quantum mechanical operators are linear. Say a cap is linear operator, then it will be the fx plus gx. These are the two functions. Operator operates on the sum of the two functions equal to a cap fx plus a cap gx. Means operator operates on this linear operator operates on the sum of two functions, and it gives the sum of operations of the two functions by this a cap separately. And the another criteria for this linear operator is that a cap and c some constant into fx, then c is constant, c will go outside of this operation a cap and fx. So these are the criteria for this linear operator. Say one example, dy dx, and here fx plus gx, and gives dy dx fx plus dy dx gx. But so dy dx is the linear operator which is obeying these conditions. Even dy dx and here 5 and fx, then also it will give 5 into dy dx into fx. But a square root is not linear operator. Say here gx plus fx, and this is not equal to root over of gx plus root over of fx. So root over is not a linear operator. Square is not a linear operator. Log e is not a linear operator. And sine, cosine, these are also not linear operators. Then quantum number, then quantum mechanical operators 2 to the commutator operator. This also plays important role in quantum mechanics operator. Say A cap is one operator and B cap is another operator. Then the commutator of these two operators is A cap, B cap minus B cap and A cap. Or in short we write third bracket A cap comma B cap. So this one is the commutator operator of this A cap and a B cap. One example I can say A cap equal to d by dx and B cap is 3x square. This is also taken as operator, and fx is equal to sin x. Then these are the two operators. I like to calculate the value of this commutator operator of this 2. Then I shall have to take one function sin x. Then it is the dy instead of A cap dy dx, and instead of B cap 3x square minus 3x square d by dx and the function sin x. So this one equal to, and this is dy dx comma and 3x square and fx equal to, or sin x equal to. So in this case, so this dy dx into 3x square sin x minus 3x square dy dx sin x. Another step I can do 6x sin x and plus 3x square into cos x dy dx on sin x gives the cos x minus 3x square into cos x. Here also this value is cos x. So this term and this term will cancel and gives 6x into sin x. Sin x is the function, so the operator, so the commutator operator of this dy dx 3x square is equal to 6x. If we change the function, if we take another function, any function, then but still then the commutator operator of these two will always remain 6x. The commutator operator has some relevancy in quantum mechanics. We know if the operators are the linear operators, as I have stated, then linear operators is quantum mechanical operators, then A cap, this operator will represent one physical property, B cap also represent another physical property, and if these two, if the commutator operator of A cap and B cap is equal to 0, then we can say A cap and B cap are commuting each other. That means if we change the order of multiplication, then the result will remain same. A cap, B cap. A cap represents one physical property, B cap represents one physical property. If these two are linear, then whenever this condition is obeyed, then the properties the operator represent are determined accurately and simultaneously without any error. Say this is y cap and this is px cap. This is the operator for the position of this particle along this y direction, and px cap is the operator for this property, linear operator along this x directions. Then this one equal to 0. It means that this position along this y-axis and the linear momentum along this x-axis could be determined simultaneously, accurately, without any error. But if we can say phi x cap and phi x cap, this is not equal to 0. It means that the physical property these two operators represent could not be determined accurately and simultaneously beyond a certain limit. In this case, the position along this x-axis and the linear momentum along the same directions could not be determined accurately and simultaneously without beyond a certain limit. So these are the relevancy of this commutator operator in quantum mechanics. Then third one, eigenvalue, eigenfunction and eigenvalues. Eigenvalue. Suppose an operator operates on a function, gives the same function multiplied by some constant quantity. Say this one is constant. This one is constant. This equation, whenever the operator operates on this function, gives the same function multiplied by some constant quantity, this equation is called eigenvalue equation. Eigenvalue equation. And this psi x is the eigenfunction of the operator A cap with eigenvalue lambda. For example, say d by dx and e to the power minus ax. A is constant. Then it will give you minus a into e to the power minus ax. It means that e to the power minus ax is an eigenfunction of this operator dy dx with eigenvalue minus a. Eigenfunction always refers to the operator. It has no absolute meaning. Say fx or the psi x equal to sine 2x. Then dy dx and sine 2x gives 2 cos 2x, means the same function is not coming after the operation. So this is dy sine 2x is not the eigenfunction of this operator dy dx. But if we write d2 by dx square and sine 2x means dy dx will be operated twice on the sine 2x. It will give minus 4 into sine 2x. Same function is coming with an eigenvalue minus 4. So sine 2x is eigenfunction of this operator with eigenvalue minus 4, though the sine 2x is not the eigenfunction of this operator dy dx. So eigenfunction always refers to this operator itself. Then fourth one. Fourth one, Hermitian operator. Hermitian operator, say eigenfunctions, two eigenfunctions of this operator will follow the such conditions. Say integration all space and psi star into a cap and phi and d tau. If this is equal to integration all space phi into a cap psi and the complex conjugate into d tau. If this condition, this is obeyed by an operator, then this operator is called Hermitian operator. Psi and phi, these two are the eigenfunctions of this operator a cap. Say one example, psi equal to e to the power ix and phi equal to sin x and d2 by dx square equal to and a cap equal to d2 by dx square. If this is the situation, as I have taken an example, then this one is psi star complex conjugate of this psi means e to the power minus ix and d2 by dx square and here phi means sin x and here dx equal to this sin x. Whenever twice differentiated with respect to x, it will give minus sin x. So minus integration e to the power minus ix and sin x dx. And the right hand side, whenever I write this sin x, phi instead of phi we write sin x and d2 by dx square and e to the power ix and star complex conjugate into dx equal to, whenever this e to the power ix is operated twice with respect to differentiated with respect to twice d by dx, this operations will give I square e to the power ix and I square means minus 1 and integration, and whenever this complex conjugate of this one will be equal to e to the power minus ix and sin x dx. So these two sides, these two same means left hand side equal to right hand side. So this d2 by dx square is a Hermitian operator. And all quantum mechanical operators are Hermitian operators. Then the properties associated with the Hermitian operator. This could be proved. This property A, eigenvalue of a Hermitian operator is always real. This is the first property. Say a cap is Hermitian operator, then psi x is a function. Hermitian operator means quantum mechanical operator. This equal to lambda, since psi x is the eigenfunctions of this A cap, it will give lambda and psi x. This lambda must be real. As the operator is Hermitian, so this operator represents some physical quantity, and this physical quantity is lambda, and physical quantity means experimentally observables, so it must be always real. And then B, eigenfunctions of a Hermitian operator corresponding to different eigenvalues, are orthogonal. Let me illustrate. Let us A cap and psi 1. A cap is Hermitian operator. Psi 1 is eigenfunction of this A cap and gives this lambda 1 into psi 1. Lambda 1 is a physical property, this is the constant. And for the same quantum mechanical system, suppose A cap and this is another function, psi 2, and gives a lambda 2, another property, and this is psi 2. If lambda 1 and lambda 2 are not equal, lambda 1 is not equal to lambda 2, then integration all space psi 1 psi 2 d tau must be equal to 0, means psi 1 psi 2 always be orthogonal. And the third one, if phi I represents a set of orthonormal means orthogonal and normalized, orthonormal eigenfunctions of a Hermitian operator, then any well-behaved wave function with the same boundary wave functions, psi would be expressed as summation of Ci and phi I. Means this one equal to C1 phi 1 plus C2 phi 2 plus C3 phi 3 and plus that. C1, C2, C3 are the contributing coefficient of a phi 1, phi 2, phi 3 towards this formulations of this psi. This property is very useful for formation of the molecular orbitals or hybridized orbitals by linear combination of atomic orbitals. So this is in short about this brief discussion about these operators and the eigenfunctions, eigenvalues. In next day, I shall in my next lecture, I shall try to discuss the 4 quantum mechanical postulates. Thank you. Thanks to you all who are watching this video, and if you like, then I request you to subscribe and share.